Good morning to all the panels. My name is Sarvesh. Today I'd like to present about my FYP studies on effects of different thickness of UAV airfoil on aerodynamic performance using CFD techniques. This study supervised by Dr. Adi Azre. Nowadays, UAV used for various missions. For fixed wing UAV, a wing is the main contributor that decides the aerodynamic characteristic of an UAV. The latest technology of wing is known as adaptive variable camber compliant wing. This wing eventually changes the wing thickness during flight based on the aerodynamic requirements. An airfoil is a 2D section of wing. Appropriate airfoil selection is a must for good aerodynamic performance. Thus, Selig 1223 airfoil have been chosen for the suitability in low Reynolds number operations and the ideal lift and drag value. Statement is the most critical flight mission of UAV is takeoff. The usual restriction UAV encounter is takeoff distance because UAV need to operate at various environments. Thus, UAV should be designed to be able to take off with short distance from any location. Therefore, further research is essential to determine the Selig S1223 airfoil effect of different thickness on UAV during takeoff condition. There are three objectives in this study. The first one is to conduct the CFD simulation of model wing and validate with the experimental data. The second one is to compare the effects of changing the thickness of the airfoil on three parameters, which is coefficient of lift, coefficient of drag, and lift to drag ratio in takeoff condition. The third one is to determine the optimum design of airfoil with respect to the takeoff condition. So, when there is a movement of air passes through a body, there will be two forces will be produced, which is known as lift and drag. The lift pushes the body upward while the drag pulls the body backward. So there are few researchers have been done earlier on morphing wings have been analyzed to determine their methodology and their findings. So based on the researchers, we have found that mostly study focuses on NACA airfoil and they really compare between airfoils. But the solid study on morphing wing is have not been done. This is the flowchart of the methodology done throughout this study. So the first methodology is geometry generation of three model which is 50% thickness, 100% thickness and 150% thickness. So this plot have been done on Airfoil tools software and the coordinates have been extracted and transferred into ISM software. So in ISM software, we did the meshing. So there are basically three types of meshing, which is known as structured, unstructured, and hybrid. So we need to compare and choose the suitable mesh based on our study. So the suitable one is structured due to its advantages. So next is the mesh done on the airfoil. So this is the mesh we have done. So basically in this study, we have chosen a C mesh. Why C mesh? Because C mesh provide better convergence and it helps to control the wall plus function of the mesh to give better result. As we can see, there are denser mesh around the airfoil. That is actually the first layer boundary thickness being chosen by us manually. So the first layer boundary thickness we need to calculate using dynamic viscosity, Reynolds number and the diameter of our model. So we get the value of first layer boundary thickness of 0.000216 meter. So once the mesh is done, the next is a mesh dependency study is a must. So since we have two different values, different parameters we need to study, which is CL and CD. So we have done for both mesh dependency and we found out that The most suitable number of element and ideal one is 2,833,000 to obtain this accurate CL and CD value. So these have been used for throughout the study. So this is the boundary condition where we have our velocity value and pressure outlet value. And the turbulence type model we use is transition SST because it is more suitable for our Reynolds number, which is 300,000, so which is in transition period. And the residual error is 10 power to negative 6, so we have a better convergence value. These are the reference value. And this is our domain setting, which is a 20 chord length. As we can see, the geometry from the domain we have been defined as the front, top and bottom of domain defined as velocity inlet, the back of domain pressure outlet, the side, both side is defined as symmetry, Airfoil is wall. So next is our result and discussion. So this is the data we extracted and validated with the wind tunnel data. So based on this, the CL we have a percentage error of 90%, 19%, and CD we have a 2%. Actually, this is still in acceptable margin because the wind tunnel actually represent the real situation, which have many concentration or errors or some other real life environment. But the simulation we done on CFD is exactly based on the theoretical model and the equation we have chosen. So there might be some differences between both of the method. So once done with that, we did simulation on our three models, and these are the values we found for the CLCD and lift to drag ratio. So based on the simulation result, the 50%, 100% and under 50% have coefficient of lift value of 0.575, 0.936 and 1.595, and CD value of 0.0066, 0.0187 and 0.0239. So compared to all the three types of model being simulated, we have found that 100% 50 thickness of wing recorded the highest coefficient of lift. So this is the pressure contour. As we can see, this pressure contour helps us to show us and illustrate the pressure differences between the upper surface and lower surface. It shows that upper surface have a low pressure and lower surface have a high pressure, which eventually will push the object to upward. This is based on the Bernoulli concept. So even we have the indication of the pressure, highest pressure value and lowest pressure value on the left hand side of this image. Conclusion of this study is basically in this study we more focus on morphing wing. So we mimic the wing thickness difference into a morphing wing during takeoff condition. That's why we analyze in zero angle of attack condition. So we done the CFD simulation and found that the Selig modified wing proof that more we increase the thickness, the more aerodynamic performance increment, which is more ideal for takeoff condition. So the 150 thickness being able to produce high lift even at low and increase the efficiency of takeoff performance because this 150 thickness of wing when it able to produce high lift it eventually can help us to take off in shorter distance, which is our objective and our problem statement. So in this study we have found that the best suitable wing is 150 thickness wing for this study. That's all. So that's for future work we have 3D printing, so we can do some wind tunnel data extraction from UPM lab. So these three models have been printed out for now. That's all for me. Thank you.